All right, hello, welcome back. I'm Brendan MacLean, the lead developer of Skyline. As maybe you've heard before, last week, have been teaching with Olga and Mina for a really long time, almost 10 years now. And yeah, I'm just gonna review quickly the data sets and what we did to them last week that Olga's already started talking about before handing things over to Mina, and she's then going to show how we would process the outputs. So give a sort of detailed dive into what Olga's been presenting. So anyway, to start, so last week we first did this this Brooder data set where what we did was we built a library, or what the experimenters did was they used DDA to, in their paper, build what we call a sample-specific library. So they just pulled the sample and then collected a bunch of, several DDA runs on just this pooled sample, and then built that into a library. And so when you think about statistical priors, the statistical prior that they had was, well, I guess I'm going to cover that. Yeah, so sample specific library. The prior that you have is everything in the library is detectable with DDA, with the same sample preparation used for DIA. So we took exactly the same sample preparation. We just run DDA on it a bunch, and then we're going to use everything, and that's as good as we're ever going to get if we use a tool like MaxQuant or some other label-free tool. In our DIA data, so in our DDA data, we can't possibly detect anything that we don't identify in MSMS. So we take that as a library, all the stuff, rather than using the DDA as our quantitative data. We take that and we apply that to DIA data, and then what we found is we can get improved, we can get more selective data, improved quantitative values to feed into a tool like MSStats. And then we also have ideally, and it was true in this case, we were able to use the same instrument for DDA and DIA, and so we have high confidence that we could detect everything in our library with DDA. We have, it's extremely likely that we'll be able to also detect it with DIA. So then the other thing that we did, and this is the data that we're going to talk about mostly today, is to take pooled data and then fractionate it chemically in some new way, so that we get a lot of new samples. In our case with the Celebsec, 42 different samples that then we ran DDA on those samples, and they're expected not to contain the full set of proteins that are in the pool. There's some chemical sample preparation has been applied, and each one of these samples now contains a subset of proteins. So we think that we ought to be able to get a deeper library. We ought to be able to get more of the proteome, but it may be that we're now detecting things, or we kind of expect that we're detecting things that we couldn't detect with the sample specific library. We couldn't detect it normally with DDA, but maybe we can detect it with DIA. So deep proteome library prior. So you can do these experiments now. You can get a deep library that somebody else has created. So it's like it was detected on their machine. In this case, everything's done on the same machine, but everything in the library is still detectable with DDA. We haven't yet gone to the level of, we could also just generate a PROSIT library, and then we would have spectra for everything. We'd have predictions for everything, but we'd have no idea whether it was actually even detectable by DDA. So we haven't quite gone that far, which would be expanding our priors to even less certain that we're going to be able to see this stuff. But so everything in the library is at least detectable by DDA. and usually with many more runs. So there's possibility as we increase the number of runs, we have, and there are plenty of papers about this in in proteomics and mass spectrometry, that as we add a bunch of different runs, we start to potentially inflate false discovery rate. So we need to be really careful about that. With 42 runs, we might actually get a lot of things that were not detectable. And then obviously it takes a lot more sample preparation if you're going to do it yourself, but you can also then rely on something that somebody else has built. But so yeah, usually for broader use, and then that, which means that if you use something that somebody else has produced, it's unlikely to have the same chromatography as your DIA, and maybe not even on the same instrument. And even in your own lab, it may not have exactly the same chromatography because it took you so many runs to build a library that you're going to bring it back months, years later and use it. So like the Aebersold produced a pan-human library, the Aebersold lab produced a pan-human library that they then used for many months to years, and it's publicly available. So then, as Olga described, there's a refinement experiment that was done by the Selevsek team where they didn't necessarily expect it to be a refinement experiment, but we used it as one, where they did these reproducibility samples, 8 of them, and they just used pooled sample and ran DIA on it. And then we can use that to screen from our big library down to, okay, well, let's go back to what we think we have a hope of detecting in this sample. And that's, and we can apply certain criteria there. So we could definitely, we could just do like, what was detectable? What was detectable at all? But we've chosen to do all detection and CV. So we do both. Is it detectable? And do we think it's got sort of stable quantification? And those are the things. This is, again, this concept of, taking very wide, a very wide starting point with RT prediction could be spectral library prediction or a big spectral library like what we have. Unrefined methods, we might have some previous measurement information, but we put it into this idea of method refinement. And then we feel that if we do that, we can have a better quantitative assay for fewer things than what we started with. So this again is that loop. And in this case, we're applying refinement of measurability and repeatability. We could do more experiments, and the more prior knowledge you build up of your samples and of the things you're trying to measure, like, does it experience degradation, digestion? Does it behave linearly? We've done all of these both on very targeted samples. So then this again is just the overview. The 2 data sets, Selevsek all, which, and Olga has just been talking about these. This is just like everything, all the noise, everything, we just throw it all into the entire library, we quantify everything, and then we take it out and give it to MS Stats and say, okay, what can you find? And then this is the refinement experiment where we take, we had a document called Selevsek reps. We imported the replicate data, the repeatability samples, and on the entire library, then we did the refinement of detectability and repeatability. And then we just used all the things that we felt were detectable and repeatable. And then we were quantifying based on those. So that's the overview of these 2 data sets that Olga's already been talking about. And then the last thing, I saw what I thought is a great question. Somebody said, oh, what's going to happen to my false negative rate? In other words, am I going to lose important signal if I do this refinement step? And my answer to that is going back to day 1 at something that Sue Abatiello presented. And this is a figure from like a book written in the 1970s, I think. So quite a while ago. But the concept is it applies to, we're in that case, Sue is applying it to mass spectrometry, but I think it just applies to statistics in general. That yes, you may be reducing your signal, but if you're reducing your noise more quickly, then your statistics are going to be based on your signal to noise. And so you may feel like, I'm losing all this signal, but you actually may be able to detect more and get better statistical results. So you always have to be thinking about how much am I introducing noise and how much am I introducing new signal or removing signal and removing noise. So, when we've had these discussions about whether we should use sample specific libraries or big wide libraries and what are the priors, frequently, I think everybody can agree that if all I do is add noise, so if all I'm doing is adding peptides that are not changing, I'm actually making my life worse. So the more I can know up front and the more I can increase my signal and reduce my noise, the better. And sometimes when I just go with bigger and bigger data sets, I'm really just adding a lot of noise. And with that, I will turn things over to Mina to sort of dive into the details of those data sets we just talked about.
Thank you, Brendan. I hope everyone can see my screen. Hello, everyone. I'm Mina Choi. I'm a senior scientist of bioinformatics at MPR department at the Genentech. As Olga mentioned, I graduated Purdue statistics department, and then doing my postdoc under the Olga at the Northeastern University. I have worked with the Olga like almost 10 years, and then also worked with the Brendan almost also maybe more than 10 years, which is really, I was really lucky. And then it is really my pleasure to join the May Institute this year again, and then introduce the MSStat. So my session, my goal is to introduce how you can use the MSStat. So previously we used the MSStat package and then command line, but this year we want to introduce the MSStat Shiny, which is the Devon develop. So let's go back to our site. So this is our session site. So I hope you already go through this installation part. And then here, if you go here, you can download the data set. So we are gonna start from the data set that what the Brendan provide. You guys already work with the Skyline to process the cell-level data and the broader data. Today, we are more focused on the cell-level data, low CV case versus all. We want to go through one of them, and then I already provide all the output, and then at the end, we want to compare. So you can download all the data set over here. So if you download everything, so you should have the cell-level the folders. Okay. In the folder, we already have this R script to install some dependency. So if you haven't started to install it, you can also use this. So let's go start from our MSStat Shiny. There are two ways you can use the MSStat Shiny application. One is from the GitHub. You can download all our source code and then run locally. And the second option is you can use the online applications. So today we are gonna work with the GitHub because online application now we have almost 80 people I guess we all of us cannot use just one application simultaneously. So let's go to the GitHub first. So this is the GitHub for MS Shiny one. So if you click here, code, you can download the zip. And then if you unzip it, you can have this folder, MS-Shiny main. And over here, you can here see the Shiny MS that are project files. And then you can double click it. Then the R Studio will be open. And then it should look like this. So I will make this one is a little bit bigger font size. All right. If you have any difficulty, please ask the question in our Q&A. So this is the how it looked like. So if you already learned R and then know about the R, this is the console, which is what we are gonna use. Okay, white background. Yes, I can. So everyone is okay so far? Right. So that, yeah, so right panel, this is the console, and then here's our script, and then here's the environment, the panel, and then this is to show the files and plot and package, etc. So we have to go to the MS-Shiny main folder, and then just double check. I will type the get working directory, and then here is where I am. If not, you can click more, this more button here, and then set as working directory. Then you're gonna start from this directory. So to run our MS-Shiny, I just opened the R script install the dependency.r files. This part is to install all the required R package. If you already did it, you can just go ahead to the row 10 library Shiny. So we are gonna set loading the Shiny the package. Then you can type run app. Then the new window will pop up for MS-Shiny applications. So this is the Shiny application, but still in the background, the still R is running, right? You can see this cursor is here, and then you can see this is stop. Stop button means the R is running. So we can see all the progress as a background in the R if you use it locally. So let's start from the MS-Shiny. This is the open homepage. They said, okay, what version of the MS-Stat, what version of the MS-Stat TMT you use. If we go back to our folder to download it, the select low CV, we are gonna work with the low CV. And then there are several files. Something is some R script and etc. But we are gonna use this output from the Skyline. So this is the MS-Stat input dash plus CSV. This is originally what the Brandon provide. However, I made the subset of the data. to save our running time. So when I run this data set, it would take 10 to 20 minutes, but this one is really faster than this one. So just using the 400 proteins. So yes, so this is how the MS-Shiny look like. Okay, so to run the MS-Shiny, what you need. So before we move on, let's go over the what exactly MSDAT workflow doing. So MSDAT is for protein abundance analysis. And then our original input is some table, which is already identified and then quantified. So we working with a lot of the data processing tools, the Skyline, the Spectronaut, OpenMS, the MaxQuant, PD, and also people ask they is working for the DIA-NN or MaxDIA, MaxDIA, etc. DIA-NN, I think the Matthias is working to make a converters.
Could you make a presentation mode because it's very small?
I want to keep it because I have to go back and forth. Yes, sorry. Yeah. You guys already have this presentation, so you can also download this file as well. Yeah. So yes, we need a data from the data processing tools as MSDAT, input plus, etc. And then most of tools we are working on it. For example, Spectronaut, there are MSDAT report scheme, which generate the MSDAT required format automatically. And then some other tools, for example, MaxQuant, we use one of the data output, the evidence, TXT, etc. So most likely we working with a lot of the data processing tools. Plus, we need one more tables we call the metadata. So these processing tools can processing and identify and quantification, etc., for all the runs, but we need experiment design information. For example, each MS run from which samples. Which sample means disease sample 1, patient 1, or healthy patient 2, etc. So this one actually we cannot get from our processing tool. This is what the researchers design. So we need to separate the metadata. We need it. How it look like is this. So we call this is the annotation template. So these three columns are required. If we are missing one of them, we actually cannot use the MSDAT. Here, for example, the run or file name for each run file ID. And then we have to tell this sample, this run from which condition and then which biological replicate. The presentation is available in the Google Drive. The Google Drive link is available in our Google Sheet here. Data available here. You click the here and then you can see all the data and then presentations. So this is how it looked like, the three columns. We have a very similar type of the metadata for the TMT. So tomorrow team will talk about the TMT case. We have more information, MS run and channels, but this is our required. So we have these files already here, annotation, CSV. And then we have quantification data here. We call the MSDAT input plus 400. If we had 2 files available, we are ready to use the MSDAT Shiny applications. So let's go to the first step. So what the first step doing is here. So this is the whole the MS Stack workflow. We have two files, and then we input this file into our MS Stack or MS Stack Shiny. There are multiple steps that happen. The first of all, we read the data and then doing some pre-processing steps. So we filter out some decoy or IRT proteins, and then share peptide, etc. If we have a multiple peaks, we also aggregate it and then filters some others, etc. This is a kind of the what we are kind of to forget about it, but this is also quite very important step to make very uniformize the data to run the further analysis. And then also we do the transformation first, the log transformation, and then normalizations. So we also perform this step. And then from here, we define the missing value and then impute the missing value and then summarize to the protein level. And then we do the testing. And also we provide the experiment design. So MSStat itself for command line wise, this is the function name. So first there are 4 big functions available, and they should run to get the our volcano plot. So first of all, if you use the Skyline, you can use the Skyline to MS the format function, and then this function perform the pre-processing step. If you use the max quant, you can use the max quant to MS the format, and then they are doing the pre-processing step customized for the max quant, etc. And then the next step is the data processing. Data processing is simple. What they're doing is they do the transformation and then normalization and then up to imputation and then up to protein summarization. So data processing function perform the whole this step. And then the group comparison is, inference, hypothesis testing, and then design sample size provide the power calculation, and then sample size calculation. So this is how the MS command line doing. And what is the MS Shiny application also have a same workflow. We have a big 4 step, each big 4 step also for each function. So data uploading, read the data, and then doing the pre-processing, and then data processing, doing the normalization and imputation, the summarizations, and then statistical inference is really inference, and the future experiment show the number of the sample, number of the biological replicate or the powers. So let's go to the data uploading, the first step. The first step, we have to upload the data. So we have to decide what type of the acquisition we are working on it. Here, click DIA. And then the DIA, what kind of tool you use, we use the Skyline. So click the Skyline. And then they just show you what the files do you need. So we needed 2 files. Here we have to upload the MSD report from the Skyline. MSD Skyline report from Skyline, click the browse. So I put, I made some folder here. So if you download everything, it should be there. And then slipsec. And then there are 2 folders, slipsec all and then slipsec low CB. We have to go to the low CB. And then low CB, you have a MS input plus and plus 400 CSV. This is the file. We're gonna working on it. And then click open. Then the next, we have to upload the annotation files. Annotation file, this annotation files. So click browse. So same location, I click the annotation CSV and then open. And then here we two files are uploaded. And then there are two options. So remove the protein with the one features or the filter with the Q values. So I recommend to use the filter with the Q value. So here, this is our default cutoff for Q value, and then click upload the data. Then it will take some time to our first step. This uploading data set, they read the data set, also goes through this processing. So when this is done, they show the summary, so how the MSDAT recognized this data set. So it is really good, important to review, especially this part, move on before you move on to the next step. So first of all, let's check number of the condition 6. Yes, 6 condition we have. And then check number of the biological replicate 3. Yes, we have a 3. Yes, number of the technical replicate. Yes, we have a 1. And then total number of MS run is 18. Yes, correct. Sometimes a very small typo or something like this, you can see the number of the MS run is wrong. Maybe 17 or so it is really good to check this one first. If you see some numbers is not correct or not is what you expected, you have to go back to the annotations or you have to double check the quantifications. So, and the next they also show the summary of the data set, the brief summaries, the brief statistics. So number of the proteins, now we have a 400 proteins are available, and then total number of the peptide, total number of the features here in case fragment level, and then also tell us the number of the peptide per protein. So 1 peptide to the 82, and then how many features per peptide we have, and then intensity rate. And then this is the how we read. This is the first, the top 6 rows we have. So if you do not see the 400 CSV file, could you double check? I uploaded a few hours ago. Maybe just refresh. So here the features means we use the peptide charge or the fragment level. We call this is the feature because it will be different by the acquisition type.
Hey, is the 400 proteins file supposed to be in the low CV subdirectory of the Google Drive?
Yes, exactly. Yes.
Is it titled just MSStats input plus, or does it have like a specific
MSStat input plus dash 400?
Yeah, I don't think it's
not there.
Yeah.
Okay. Sorry about this. Okay. Can you see now?
Yeah, I see it in there now.
Thank you. Sorry for my mistake. Okay, so then, I can wait. I can just talk about a little bit more while you guys just start to uploading. So here, let's talk about the annotation template. So the kind of the concept for MSStat, Olga already talked about there are some other tools to do the same purpose. And then, other hypothesis testing part. And then I also feel from our Q&A, people ask the MSStat provide the t-test, MSStat provide ANOVA, etc. So I know the other tools, they provide several different ways to do it. For example, Perseus, they provide a t-test, ANOVA, etc. So you can customize it. You can decide what kind of model you want. But in other way around, depending on what you choose, the model, the result will be different, conclusion will be different. And then sometimes the statistical knowledge required to define the right models. So MSStat, the philosophy I start with is we want to minimize the user's decisions, especially the modeling, statistical model wise. So our goal is we do not provide the multiple way. We do not provide ANOVA. We do not provide the t-test, but let the MSStat recognize what is the best model for your data set. And then we are gonna use the best model for your data set. So that is the kind of the main goal, which means the user have to tell them what the design we have, how the experiment design look like. So annotation is the place you can tell how your design look like. So we also talk about, we also talk about the linear models or ANOVA, etc. And then, yeah, we talk about the factorial design, etc. There are several different types of the design. So we clustered the two different designs. One is the case control design, and the other design is a repeated measurement design. So for example, case control design, let's say if you have two groups, healthy group and then cancer group, and then cancer group, let's say 10 patient, and the healthy group, we have a 10 patient. This 10 patient and 10 patient cannot be overlap each other, right? The cancer patient cannot be the healthy patient. Healthy subject cannot be the cancer subject. So it will be very unique, like the unique 10 subject, unique 10 subject, and then want to compare. We call this is the case control design. Then we have to tell them they are unique. How we can tell them based on the biological replicate. Biological replicate, this column should be unique. Here we label 1 to 18. It doesn't matter A, B, C, D, E, F. Just matter is how unique or not. The repeated measurement, sometimes it happens the time course and the pair design. So for example, let's talk about the pair design first. We have a healthy and then the cancer group. However, we actually take the two samples from the one subject, right? So the biological replicate is the same, the patient A, but we take the healthy tissue from the healthy tissue, and then we take the cancer tissue. So two different conditions, two different samples, but we have a same biological replicate, the subject. In that cases, we can label this one is the same. So for example, here, 1, 1, we have a one subject, but we have a different condition. So if this is the same run and the same design, but depending on how we define this biological replicate column, and actually MSStat use the different models. For example, here, everything is the same, just the annotation file is a different. But MSStat recognize this one is the time course or pair design, and then the other one is a case control. And then we did select the different model. Here we consider subject as a random effect, and then apply this one, and then result will be different. So I always want to tell the annotation file is important, and then how you define the biological replicator is a key part of using the right the linear models. This is also same for the TMT case as well. So I think everyone can load the 400 data set, I guess. Yeah. So we are gonna do the Shiny application using the Shiny application. If time allowed, I will show you the R Studio, R code command line base, but all the command line script is already available in the Google Drive. So let's come back. So they wrote, and then we finished the data processing, data uploading part. And then here's the button, next step. So click the next step. And then what is the next step part? The next step part is the processing, data processing part, which perform the log transformation. So our log2 is our default. And then normalization, we have several options: known normalization, equalize the median, and the quantile, and then Glover standard. We have a lot of the question about this normalization method in the Q&A. To summarize it, all the answers, none. We have a none option, which means we do not perform any extra normalizations. So if you prefer to your manual normalization, definitely yes, you can do it, and then select the none, and then we do not perform any additional normalizations. Median, equalize the median is our default, is our recommendation to make a median value equal. And then quantile normalization is make all the distribution of intensity across a sample are same. This is actually from the genomics data, and then I think this one is the more appropriate for the genomics data, because the proteomics data, most likely what I can see, they have a really skewed at the lower abundance one. And then we want to keep this lower abundance as much as possible to decide the cutoff, the limit of the quantification level, and then imputation. But if we apply the quantile normalization, actually they manipulate and then add much more the bias in the lower abundance one. So I don't prefer to use the quantile case, especially DDA case. And then we have a Glover standard normalization, which means we can define what is our standard. So we can define, we can give them specific peptide or protein name, which should be standard. We know it should be same across the MS-1. So if we use spike some proteins to control it, you can use these normalizations. But let's say now we can use this equalized median options. The other option, we have several options about what kind of the feature we use. The first one is use all features. DIA cases sometimes is really extreme case of thousands of the features per proteins are available, which is kind of computationally is not that efficient, and then we do not gain much using the older features. In cases we can click use the top end features, maybe the 100 or 200, which is really a lot, or you can also use the 10 or the 30 features. You can move around here, but this case I will use the all features. For the missing value, we talk about the imputations. We are gonna impute not random missing value or the sensor value, but how do we know it? That is the key part. We are lean on the data processing. We are lean on the processing tools, and each processing tools provide a different identification or protein identifications. And also some tools provide some extra informations. And then some tools provide NA as a missing. Some tools provide a 0 as a for the missing value, etc. So you have to decide which one is we have to use it. Skyline is we treat 0 is the missing value. So Skyline provide several more information than others. For example, truncated peak. So Skyline provide us that peak is a truncated or not. So in case of the truncated peak, that is not the censored, and then not the random, more the technical, not the censored missing. This is a more technical or the random missing one. So we can distinguish this truncated peak or really the censored missing one. So the random missing we treat it as NA, but the censored one we treat it as 0 or very low value, and then we impute these values. And then this one is the max quantifier center, how we define the censored. That is the base on the whole the distribution as to what Olga mentioned. We use the cutoff for 9.999, and then we are gonna sacrifice 0.1 quantile value as a missing value, and then we are gonna impute it. So, and then the imputation option, that is our default. The default is we are gonna do the model-based imputation that performs in the feature level, not the protein level. But if you don't want, we just want to keep it, you can uncheck it, and then the imputation will be not performed. But let's keep our imputation options. At the end, the summarization, our default Tukey medium polish the summarization. And there's another options, remove the round with over 50% missing value. This is rarely happen, but if there are more than 50% missing, the Tukey medium pollution, etc., is not the ideal or the other cases. So in cases, you can click it and then you can remove the runs, which means that specific run, we don't have any the protein, the quantifications. Then click run protein summarizations. And then it showed the some progress bar here, but in the R as a background, you can also see the whole the progress. This is the how you can also get this one from the log file to track the what kind of steps go through it. For example, here, yes, the feature 1 or 2 are across the remove. The fraction is already handles. Missing value mark and as an NA. Here, like this much intensity are 0 or less than 1, which will be imputed. Low, this is low under cutoff 8.29. The log 2 intensity level less than this value, we assume this is the sensor and then will be imputed, etc. Yes, so normalization is done in the feature levels. Yes, normalization. Here we go. So normalization based on the whole distribution of the intensity before in the hour the protein levels. What is the cutoff for censored? We decide what missing value will be imputed. The 2-step. First step is based on the spectra data processing tools. They provide NA or 0. We think this is also missing value, and then we are gonna impute it. However, I guess Olga already showed some slide here. For example, this case, we checked all in the distribution of the old intensity. sometimes they have a really skewed, there are really lower abundance one. So it could be noise, it could be, or really, small value. And then we defined under there's some, this lower long tail, we defined this one is really low, it's not accurate, because it's a lower than limit of the quantification. So we define this cutoff based on this distribution. This is the kind of the cutoff for what we talk about it. Yes. So when this is done, our all the progress bar is gone, and then it shows some result. So summarize the result is update the summarize result, and then show us the protein quant. What is the second step? Here, our second step is the data processing. At the end, what we can get, this is our output. We can get the protein quantification after imputation, normalization, and the imputation. We can get the protein quantifications. So we have a quantification, protein level summarization, and then this is how it shows. So for example, here, the protein R00406, this is the condition 1, and then biological replicate 1. This is our protein quant, and then this is for the other sample, and this one is for the other sample, etc. So this one, you can download it. If you download it, you can just define the file name. You can change the file name and then save. You can save this one. But I like to show this summarization plot. So before we move on to the inference stage, we can actually see how the data look like. This one is to show the provide the visualization. So first of all, quality control plot. What kind of all the proteins? This is how it look like. So this is the after normalization. Now this median value. So each box is whole intensity across the whole the protein for one each runs. And then now this median value is equal. That's because we used to equalize the median, the method, right? And the next step, so we can also double check that our normalizations work or not. And then here you can see here, there are some the zero values, which is the missing value. And then you can see this, we have some long tail at the lower abundance cases, right? And the next one is the profile. The proteins show us each protein level, how the data look like. So there are several options. So let's say transition level, and then show the plot. You can select what protein you want to see. So let's click the first one. Then, okay, there are so many features. There are 34 features, and there's so many the features there. So they actually cut off the real one. So then this is to show the whole the transition legend. The legend is so big. So let's remove the legend smaller. So peptide level legend. So now we can show all the, feature level legend is gone, and then show the peptide level. So now you can see which color for which peptide, but still also big. And then click here. So no feature legend. So I want to remove this, want to focus on more the visualization here. Then now all the legend is gone, but actually show us how original the data look like for this protein. And then this is the feature level. And then we already summarized by protein level. Then click show protein summary. Then it showed, okay, based on the whole the features, this red dot is our protein quantification. And then we are gonna use this, not the gray line, we are gonna use this red dot for the next step. And you can also play around the other You can also play around the others. You can see other proteins. For example, here, this specific protein, some specific feature is completely missing for this one. You can go over other proteins as well. And then click saved this plot, and then you're gonna save as a PDF. So you can keep any of the proteins you are interested in. So here, download the data sets. So here, after this, we can download the feature level data. Let's download the feature level data and then look. So feature level data, I just download, or I can download into our folders. I can go to our folder, no CV. Okay, save. And then you can also download the protein level data as well. So go to our same locations. So here, so we have a feature level data, and then we have a protein level data. So let's open it. So this is how the protein level data look like. It show some information. So for example, here, protein 1. Okay, I can make this one is big. Yes, so for example here, protein R00406 for this original run, group time point 0 and subject 1, their protein quant is 15.218, something like this. And then to get these numbers, total group measurement, there are 54. And then what is the number of the features they have is 18 features. And then there are no missing value. And then this is how we get it. And let's say here these proteins. So this protein for the first subject, and then this group, this is the protein quant we have. Originally total to 270, but this sample, there are 84 features, and then like this much, percentage of missing value. So you can see this information from the protein level data. Okay, so now we are done for these steps. So let's move on to the next step. Next step is the inference stage, the really testing stage. So click the next step. That is the statistical, the inference step. So here, this part is the important part. We have to say what kind of the comparison do you want? And already this Shiny has all the condition information. They know there are 6 conditions, but how you want to define it. So there are several options. The first one, all possible pairwise comparison. Let's click it and then submit it. And then it showed all the possible pairwise comparison. So for example, here, time point 0 versus time point 15. And then time point 0 versus the 13, etc. And then 15 versus the 30, 15 versus the 60, etc. And they show how the contrast metrics look like. What is this means is this is how the contrast matrix means. Let's say we want to compare time point 0 versus the 120 minutes. We defined like here, the 1 and then -1, and then other thing is 0. How? This is the number, is a constant for each condition. So for example, here, constant -1 times time point 0, and then 0 times time point 15, etc. And then the time point 120 minutes, the constant is the 1. And then we times the 0, so we can remove all the middle terms. And then what the left is T120 minus T0, the controls. So if we define the same one, but if we just flip it, if you change the hour constant, here's the 1 and the -1. In that cases, the middle one is also, we completely remove it. And then what happened is, okay, this is the, I made a mistake here. This is the time point 0 minus time point 120 minutes. This is the how we defined. So let's come back to the hour contrast, the metric. So this is a kind of the what automatically defined it. But for most likely the 0 point is our control. And then we want to put this control to the second part, the later, right? We want to compare how much increasing, how much decreasing. For them, the 0 should be the later. So I don't like it. I just don't like this one. So I just clear the metrics. And then what is the second options? Click the compare all against 1. So we can tell against 1. So we can tell which one is our control. So here, time point 0 is our control, and then submit it. They calculate, they define the comparison against our control. So for example, here, 15 minus our time point 0, and then 13 versus the time point 0, etc. So this is the kind of the reasonable and the easy to interpret it. So I'm gonna go this one, but I will talk to you about something else. So let's practice other options. Create the customized pairwise comparison. We can actually create it. So for example, here, this is versus the 2. So 2 will be denominator part. So I said 0, and then I want to compare just 15, and then add, and then they're gonna add the 15 time versus 0 minute. And then we can also add here 120 minutes versus 0 time, and then click add, and then here, etc. So you can add, or you can just customize your comparison metrics. But there's another way we can create it. We can actually keep them the constant. So previously, this 3-1 is always we can compare the two pairs, one versus the others, one versus others. But sometimes if we have a more complex design, for example, I want to compare mean of the two condition versus others, our constant should be the different. So for example, here's our control, it should be -1. But I want to compare mean of these two condition versus the others. And then you can 0.5 and then 0.5, but we have to define it. So for example, mean of the 15 and 13 versus T0, and then click add. They can add more to customize the comparisons. So this is the how you can play around for your experiment. But I like this one. I just want to compare all the other time point against time point 0. So then after we define our contrast matrix, click start, and then they're gonna start to compare. what they are doing based on the annotation, based on how they recognize the design. They find the best model for your design and then apply and then calculate all the values here. So when it's done, okay, here they show the result. So this result panel only shows the significant one based on this cutoff. So now we want to significant level less than 0.05. So based on this adjusted p-values, you can also play around. You can order it. Like here, so zero is not really zero. It's a really small value, but this is how you can sort it. Maybe you can check this one is 0.0492. It's really close to 0.05. This is how they show it. But you can also download everything. See here, click download, download all the model widget. And then here, so let's say I just want to save this one to our folders. Okay, so not the download here. Slapsec, oh yes, Slapsec low CV and save. Yes, here, test result we have. So this is the result. So let's look at this. So for example, here, protein 1, protein R00406 for this comparison, 0 time versus the 15 minutes. This is the hour log to 4 change, and then standard error, p-value, degree of freedom, and adjust p-value, and then NA is no issues. And then the missing percentage is 0. There's no missing values. But here, these proteins for 16 minutes versus 0 minute, here's the hour adjusted p-value, but there are 1% is missing value. So this missing value means the fetal level of the missing value. Now here issue is everything is NA, but if one specific condition is completely missing, for example here, 15 minutes versus the 0 minute, if the 15 minutes is completely missing, they cannot calculate log for change or standard error, etc. So only the measurement available in the 0 minutes, we cannot calculate anything. So here all should be NA, but issue say the one condition is missing. Or sometimes it's a rare case, but if two conditions both are missing, they say completely missing. So this is how you can see the result. This is how we result, but we also provide some visualization tools. So there are several visualization tools, the volcano plot and heat map and comparison plot. The volcano plot, let's say if you click all, you can save as a PDF, but it will not showing in the Shiny application. But you can select the one condition, let's say the 120 minute versus a 0, and then click the view plot in browsers. Now you can see the volcano plot here. You can also click apply the specific 4 chain cutoff. Here, 4 change cutoff 1 is the log 2 level. This is a 0. So I said the 2 4 changes. Now they are only marked higher or lower than 2-fold changes. This one is interactive. So now here, bottom there, click the plot for details. If you click this dot, they show that this dot is for which proteins. This proteins, and then show the log for changes for which comparison, and then I'll just p-value. I click one, and then you can see this one is for which proteins. And let's say we can click this one too, you can see here. Or you can also click the display the protein name, and then they just show the whatever the labeled up or down regulated one, they labeled that is for which proteins. And then the other one is the comparison plot, also quite interested in. So comparison plot is for each proteins. So each protein, they just want to see across the whole the comparison how it look like. So here we have a one to say for 5 comparison, and then compare to our control. So here can see the hour trend. Here's a 15 minutes after, and then this is a 30 minutes after, and then this is the 16 minute after, and then 9 minute after, and then 120 minute after. You can see the whole trend, and then the dot is the log 4 changes, and then bar is the error bars. And then you can also change the which protein you want to draw it. And then, for example, this case is actually they are decreasing, etc. So, and you can also save as a PDF. That is the testing part. And then after testing part is done, we already calculate all the variance component from the models. And then based on this variation, we can actually calculate the powers and then sample size calculation. This is our last step, the future experiment. So click next step. So there are 2 options. Which one do you want to estimate? Sample size or power? Click the sample size. And then you can see, share. So because the sample size we want to sample size, this one is inactive. You can say, I want to increase the power to 90%. And then this is our force discovery rate, what I want. And then this is the desire for changes. So for example, here, if your desire for change is 1.5 with the 90% power going up, and then see, you need a 2 replicate per conditions. If your desire for change is 1.3 with the 90% of the power, let's check going up, you need a 5 biological replicate per conditions. And definitely, and here you can see these numbers as well. So Y, Y4, Y, etc. And then you can download the this plot as well. Also, you can calculate the powers. So now how many samples we have? So now we have 3 samples, right? The 3 per condition. And then this is our discovery rate, and then desire for changes. So this is the power for 1.4 desire for changes. Here, now we have a 90%, the power we have. And then you can also download it, this plot. So this is the whole the workflow when you use the MSTED, the Shiny applications. Okay, so then now we have some minutes. So after we close it, let's see, let's go over how we can run in the command line. So go to the our folders, left select, and then load CB1, load CB folder. You have here R script. the low CVR script. It also performed the same things as what we talk about it. Advantage is you can see the more option on it, and then you can see the more intermediate result. For examples, you can also have a lot of the customization one, but this is the main thing's the same. Skyline to MSDAT format, this is what we are doing, the pre-processing step. Next step, data process, doing the normalization and then imputation and then summarization. Then all the visualization with what we show, the QC, and then profile plot. And then we can also use the contrast matrix and then the group comparison part here. And also visualization for volcano plot. And here the design sample size part. You can also go through, you can use the command line based the MSDAT as well. Okay, so for example, we use the 400 one, which include the 400 protein, but I remove it. We already have this MSDAT input plus a CSV file, including the whole the data set. So let me just try to show you how it looked like. So first of all, we have to call the MSDAT here. And then we have to read this file, which is the original file, the low CV file. Okay, so I have to define my working directory here. So under the /sec low CV. So previously we worked with the data set with only 400. But original, this low CV data has more than 2,000 proteins here. So I just double checked how many unique protein name in this file. So low CV is a 2,078 proteins are there. And then if you see this all /sec all also have a same thing. So you have a R script and then you already have a output and everything. And then this one is from the all case. It has more than 3,000, almost 4,000 proteins are there. And then it took longer, much longer than the low CV case. But all the output are there. You can also see and then play around. For example, visualization for protein plot. If you use the command line, you can save all the protein, the profile plot. So now you can see here, there are more than 2,000 pages there. Each pages have all the protein information. So you can scroll and then see how it looks like, or you can searching it if you have a very specific proteins you're interested in. So you can play around here. At the end, I want to show you how much is different the low CV cases in all cases. But before I move on, do you have any questions? I think the Devon already answered all of the questions. Sometimes after summarization, the protein level distribution of each sample is not even. yes, do you think that we should do another normalization at the protein level? I prefer not. So for me, the normalization, what is the goal for normalization for this step is just want to remove the systematic errors, right? Um, when we normalize and the multiple step of the processing is important, but it will be very, we have to aware of too many processing step actually can ruin the data. So that's why the normalization is a really key part. And that sometimes if our assumption for each normalization is not suitable for your case, actually you can completely ruin the data. One of the example is, IP experiment. IP experiment is, we talk about the whole the protein, global protein profiling. So we just quantified all the protein in the samples. But IP case is quite different, right? We have a bead and then we actually grab the whatever interact. And then there, first of all, the total quant of the protein is different. And then their level also really different. But what we are proposing, the normalization, especially the equalized media and then quantile normalization, we have assumption, we have a larger number of the sample, the intensity, and then the majority should be equal. Majority should be not changed across the sample. So based on this assumption, we can do it. However, for example, IP case, this assumption is not suitable anymore, so we should not use these normalizations. So multiple step normalization also very good. So we can do the many processing step, but so many processing step also can ruin the data set. So we have to be careful. And then for me, the normalization step, this normalization just to remove the systematic error, and then we want to keep the other variants as much as possible. So protein level, my question is the protein level distribution should be equal. More the feature level is original our data set, and the much more variant, the much more the intensities are there. I think that one is more suitable, but the protein level still I have a question mark, and then prefer to minimize our. It's hard to make some balance, but I try to keep the feature level and then do not perform the protein level the normalizations. So compare the MSTED and the PERSUS. So that is really the good question and the most common. So as I mentioned, the PERSUS and the MSTED have a different philosophy. The PERSUS is really GUI software, right? The PERSUS, you can do many things. You can customize it. You can do t-tests, ANOVA, and many things you can select it. And then they also provide some linear model, but you have to define what is the best for yours, which means they have a lot of the flexibility, but still need the statistical knowledge to make a right decision. And then sometimes we have the diagnosis too. So MSTAT do not provide a multiple way, but we want to provide the best without your decisions. So it is really hard because MSTAT have only one best model, but PERSUS, they have a multiple output can be conclusion we can have it. So I think this is not the fair enough. Definitely they have a pros and cons, but it's really hard to compare the performance itself. So, and then IP experiment, you need to first remove the background. So IP1, so right, so IP1 is there are several ways. So this one is we have a think about the different ways. So as I mentioned, all the MSTAT background, our baseline is based on the global proteome profiling, right? Not based on for IP case, right? So we can think about some different way because this one is actually there. Yes, there are some some proteins are there or not, right? The more MSTAT on the relative scale, we can compare to how much their difference. But it is not the suitable for yes, they have it, yes, or yes, they have a proteins are there or not, right? So there are some other the tools are there. The Saint is also quite popular for these cases, even though they used some different one. They used a spectral count, not the intensity, right? So that's why you have to know like what kind of tools doing something and so on. So IP cases is a little bit tricky, and then it's hard to follow the general workflow, the MSTAT, in terms of the normalization, how to remove, etc. In the case, I also recommend to you can also double check the other tools, for example, the Saint as well. Okay, so we have a 5 minutes. I can show you. This is not the MS at all. This is more R. And then this is how this, their data is different. I try to make a simple code as much as possible. So let's go to the SelectSec folder first. Click and then set the working directory. So we have to install this deployer one. So first two line, we call the two data. So one is from the all SelectSec, and then the other one we from the low CV case. And then let's grab and then just run it. So now this the test have a both data set, and then want to compare. The first one, I want to compare how many the significant proteins are available for both case, and then how much different number of the significant proteins are there. So from test, based on this cutoff, I just run here. This is how it look like. So for first comparison, 15 minute versus a 0 minute, all have a 33 proteins are significant, but low CV have a 47. And then here you can see the numbers are the different, right? All cases have always more, except the first case, right? Okay, this is the number, but this is really 33 all are significant in the low CV, or how much they are overlapping, how much they have a same conclusion. So we can check this one from the Venn diagram. So here, for example, I grabbed this third comparison, the T3 versus the DT, the time point 0, which should be the all have a 454 and then low have a 399. And then I want to check how much are there overlap. So there are 3 different ways, just how we make a visualization. The first one from the gplot function call, and then the function called Venn. Here it is. Number wise look like around 50 proteins are different. However, when we actually check this Venn diagram, here there are only 215 proteins are same conclusion, but the other one is unique. So they have a pretty much like 30-40% are different conclusions. And okay, here, this is the very simple one, but the other tools, GGVNN, something, some other package make some colors and then can show some different visualization, and they show the percentage. They said only 42% is overlap, and then 30% and 25% is they are unique. So this is kind of the what I can see is. And then, I was interested, okay, then what is this unique case? What is this unique case, right? So this is how I just check it. I just grabbed the T3 versus T0 comparison. And then show it. For example, this proteins is not significant in all, but this one is significant in the low CV, etc. So I just grabbed some cases here. YAL061W, this one. Definitely they have a different conclusion. The first one is really not significant. The second one is kind of the borderline. But the second one, the low CB, the first one from the all, and then the low CB, no missing, all they have almost a 70% missing. And then even the log 4 changes, the direction is different. This is the minus directions, up down regulation, but this one is up regulations. So this is the kind of the what we can double check. So when you find these cases, what you can do it, you can double check the profile plot, and then actually you can go back to the Skyline file, and then you can just digging into how it look like, how the chromatography look like, or is there something you can see, etc. So this is the last item. So I want to share how to compare, and then the script is also available in the Google Drive. Okay, so this is all the items I covered. I will stay here 5 or 10 minutes more. So please ask a question if you have. If not, thank you for attending today's session. So tomorrow the team and then Devon will coming back for the TMT. And then the Thursday I will come back to talk about how we can submit our data set in the public repository. Thank you, everyone. So I have a question about the technical replicates, right? So technical replicate, we are not merging technical replicate to the subject. We keep the technical replicate sample and they use the model. This is the best case. So we are not summarize the technical replicate to the sample case. So let's go back to our annotation. We recognize the technical replicate in our annotations. So here we go. So now let's say one condition and then replicate and then run. So we should have always run should be unique. But let's say we have a technical replicate for this one. How we define it? So technical replicate means we have a same condition, the same biological replicate, but run ID should be different, right? So it should be something 2, right? So which means if we have a one condition for one biological replicate, for example, here, if you have a 2 run, we recognize this is the technical replicate, and then keep it as much as possible. And then we just keep it as a protein quantification, and then consider this in the inference step, the hypothesis testing step. Oh, yeah, I'm not sharing. Okay. Sorry about this. Yeah, here we go. Okay, I will repeat this one again. The last part, let's say this condition and then this biological replicate, we assume that we have a technical replicate, which means this is the same, but the run is the different. So same biological replicate, same condition. If it have a multiple run, we assume this is the technical replicate. Another story we have, if we have a fractions, we can have it. If you have a fraction column is required. We need to define the fractions. Fraction 1 and 2. Then they said this is not a technical replicate, this is a fraction. But without the fractions, if we have a multiple run, this is the technical replicate. Do you have any other questions? Yeah, and if you have an error or any suggestion about the master shiny, something not working and then something is not what we expected, please report to MS Google group, and then Devin and then Matthias can help, and then it will be also help to fix the bug. Devin, do you have any kind of the most common question we can mention?
Not really. I think a lot of people have been having some trouble installing the package.
Installing?
Yeah, so just what I would say, if you're on Windows, because the new version of MS Stats requires you to compile some C++ code, if you're on Windows, make sure you install RTools as well, along with R4.2 and MS Stats. And like once you install RTools, everything should be able to install correctly. But that's, yeah, I think that would clear up a lot of problems.
Thank you. Yes, so command line scripts there, Shiny works. Yeah, if you have a big data set, if you have your own DIA data set, I recommend to use the locally, not use our online applications. Right, the MS the Shiny can do the step for the peptide level. Need us some data manipulations. So we have a two input. We need a annotation input and the quantification input. The quantification input, there are protein name column. If you replace this protein name column for the peptide, and they actually running with the peptide levels. Okay, so new questions. Batch effect. Simple answer, no. So you have to do your manual work to fix the batch effect. Right, so MS that we try to find the best model based on our frame, but the cons is it's not that much flexible. So if you have like some, for example, date effect, some other the batch effect, cohort effect, it is not that flexible. You can apply apply this variable in the linear model. In the cases, I recommend to use the lemma from the protein quant. So up to here, data processing, you can use them as that. Then later, you can use some other method. Yeah, we have 24 people. I hope they're running. They're running the Our Shiny. I have one question. I think I don't understand the question. Could you rephrase again? Philosopher. Deva, do you have any idea about the philosopher?
Yeah, I think it was actually just added
Just
in the
added?
new version of MSStats TMT. I'm not sure if there's, actually, I think it's available now for base MSStats and MSStats TMT,
Okay.
just
Mhm.
recently.
Mm-hmm. DIANN is coming, right, Devin? DIANN. DIANN.
I'm not sure.
Sure.
Yeah, I'm not positive about that.
Mm-hmm. So most current MSStat is a 4.4, right? Not 4.2.
Yeah, it's 4.4.2, I
4.2.
think, exactly.
So let me check MSStat. I think philosopher MSStat base not yet.
Oh, okay. Yeah, I
Mhm.
just found it in TMT, so it's
TMT.
definitely in TMT. I thought that it used base MSStats functions, but maybe it doesn't. Yeah, it's definitely in TMT though.
Mm-hmm. Yes, TMT, OpenMS. Yeah, maybe the team will give it the right answer tomorrow.
Yeah.
Yeah, spectrum mine. Yeah, philosopher, yes. Yes. Philosopher, yes. Yes. if we don't have any questions, then I will let you go. Thank you again, everyone. And then see you soon, tomorrow or the Thursday. Bye.